Hi everyone. In the previous session we have studied about the definition of the embedded system, difference between general purpose and embedded system, and some of the classification of embedded system and some of the major application of the embedded system. In this session we have to study about the elements of an embedded system, core of embedded system, difference between the microprocessor versus microcontroller, and difference between the RISC versus CISC, and the difference between the Harvard versus von Neumann architecture. These are all the content of this session. Okay, we have to study one by one. Before studying that, we have to glance the classification of embedded system. We are studied only, it is based on the generation and complexity, and these are the other classification of the embedded system. It is based on the performance, or based on the triggering, or based on the deterministic. Okay, these are the some other classification of the embedded system. Okay, let's glance it. Okay, next go for the elements of an embedded system. First, see the blocks in the which are present in the elements of an embedded system. Which are the blocks present in the elements of an embedded system? System core, which is main part of the elements of an embedded system, which is also called heart of the embedded system, which it contains the microprocessor or microcontroller. Okay, and the other microprocessor or microcontroller, it uses the FPGA, ASCII or DSP or SOC. FPGA means Field Programmable Gate Array, where ASCII means Application Specific Integrated Circuit, and DSP is Digital Signaling Processing, and SOC is System on Chip. These are all present in the system core. Okay, then memory. Memory is used for storing purpose, which is connected to the system core, and this memory contains the program code which we have to run, and it is connected to the embedded firmware, which is software. Firmware means software. Okay, and again the system core is connected to the input ports and the output ports of the embedded system. Okay, then this overall embedded system is connected to the real world for communication purpose. For communication purpose, we are connecting the embedded system to the real world. This is what the block diagram of the elements of an embedded system. The core of the embedded system falls into any one of the following categories. It may be the general purpose and domain specific processor. This contains the microprocessor and microcontroller. These are the two core used for core of the embedded system. Core means when the core input is given to the core, then it process and given as the output. This is what the core of the embedded system, and it also contains the DSP, digital signal processing, and it uses the programmable logic devices. Programmable logic devices means AND or gate. Some of the gates are used in this program. Okay, and application specific integrated circuit. Application specific integrated circuit means some of the ICs are used for specific function, that is called ASCIIs. Then it is also used for commercial purpose. Okay, before studying, then go for the difference between the microprocessor and microcontroller. Before studying the difference, now we have to see the block diagram of the microprocessor and microcontroller. Okay, see, microprocessor contains the ALU, CPU and some of the register and control unit, where microcontroller contains the CPU, IO ports and contents and timers, RAM and ROM, where RAM and ROM are extra in the microcontroller, but they are not present in the microprocessor, which we have to connect in the microprocessor. We have to use the external connection. By using the bus, we have to connect the RAM and ROM, and some of the crystals also we have to connect to the microprocessor. Then see the what are the difference between the microprocessor and microcontroller. First difference is this microprocessor consists of a CPU, performance arithmetic and logical operation, where in the microprocessor arithmetic functions are occur. Example for this is Intel 8086 microprocessor. In the microcontroller, highly integrated chip contains CPU, RAM on chip, ROM or flash memory, I/O ports. Which are extra in the microcontroller? RAM and ROM are present in the microcontroller. Okay. Example for the microcontroller is Intel 8051 microcontroller. Okay, next difference is it is mainly used in personal computers. This microprocessor used in the personal computers, and microcontroller is used in the embedded system. Okay, and the complex and expensive. This microprocessor is complex and expensive, and number of instructions are more in the microprocessor. In the microcontroller it is simple and inexpensive. The number of instructions are also less in the microcontroller. Okay, it dependent unit. This is dependent unit which is microprocessor. This microcontroller is self-contained unit. This microprocessor consumes more power, where microcontroller consumes less power. Limited power saving options are available in the microprocessor, where it includes lots of power saving features in the microcontroller. And architecture is, this microprocessor architecture is based on the von Neumann model, whereas the architecture of microcontroller is based on the Harvard architecture. These are von Neumann and Harvard. We have to study in the next topic. Okay, what is von Neumann and Harvard? In the next topic we have to study those topics. Okay, and this microprocessor uses an external bus to interface to RAM and ROM, where it is in the microcontroller uses an internal controlling buses. These are all what the difference between the microprocessor and microcontroller. Okay, next go for the difference between the RISC and CISC. Okay, RISC means it is reduced instruction set computer, where CISC means it is complex instruction set computer. Okay, reduced instruction means there are less number of instructions present in the RISC. In the CISC, number of instructions are more in the CISC. Okay, we have to study one by one. Reduced instruction set computer, where complex instruction set computer, and it is software centric design and it is hardware centric. This RISC consumes low power. Low power consumption will be occur in RISC, where CISC consumes more power, high power consumption, and it requires more RAM. RISC requires more RAM, CISC requires minimum amount of RAM, and simple decoding of instructions in the RISC, where complex decoding of instruction in the CISC. Processor are highly pipelined, where processor are not pipelined or less pipelined. Execution time is very less in RISC, where execution time is very high in CISC. Uses a multiple register. RISC uses multiple register, where CISC uses single register. And RISC does not require external memory for calculation, and CISC requires external memory for calculation. And compound addressing mode is used in the RISC, where limited addressing mode is used in the CISC. And the CISC architecture can be used with high-end application, where CISC architecture can be used with low-end application. High-end application means telecommunication, image processing. These are all high-end application, where low-end applications are home automobiles and consumer goods or security system. These are all low-end application. And RISC is small code size, where CISC is large code size. And fixed number of instruction format, it is RISC is fixed number of instruction format, where CISC varies the instruction format. And example for the RISC are ARM, PIC and Power Architecture, Alpha, AVR, ARC and the Spark. These are all example for RISC, where the examples of CISC are VAX, Motorola 68,000 family, System Bar 360, AMD and the Intel x86 CPU. These are all example for CISC. Okay. Next, go for the difference between the von Neumann architecture and Harvard architecture. First, we have to see the diagrams of von Neumann architecture and Harvard architecture. See the diagram of the both. First, in von Neumann architecture, only single data bus is used to connect the other devices, where in the Harvard architecture, different buses are used to connect the devices. This is what the main difference in the von Neumann architecture and Harvard architecture. Now we have to study what are all the difference one by one. This von Neumann architecture, it is ancient computer architecture. In the ancient time, we are using this von Neumann architecture. Nowadays, this modern computer uses Harvard architecture. And CPU is connected data memory and program memory by a single memory. This CPU is connected by single memory, where in the Harvard, CPU is connected data memory and program memory separately. Okay. CPU cannot access instruction and data at the same time. The CPU cannot access instruction and data at the same time. Cannot access. But in the Harvard, it access the instruction and data at the same time. And same physical memory address is used for instruction and data. Separate physical memory address is used for instruction and data, where common bus is used for data and instruction transfer. In the von Neumann, single bus is used to transfer the data, where in the separate buses are used in the Harvard architecture for transferring the data. Okay. The speed of execution is slower in the von Neumann architecture because of single bus. We are using the single bus, therefore the speed is less in von Neumann architecture. The speed is faster in Harvard architecture because separate buses are used. Then the fetching of data is easy in Harvard architecture. The fetching of data is complex in the von Neumann architecture. Okay. And it is cheaper in cost. Von Neumann architecture is cheaper in cost and it is costly. It requires less hardware but low performance. This von Neumann architecture requires less hardware but low performance. But this Harvard architecture requires more hardware but high performance. Performance of the von Neumann is less compared to the Harvard architecture. And this von Neumann architecture is used in the personal computer and small computers, where Harvard architecture is used in the microcontrollers and digital signal processing. Okay. These are all the difference between the von Neumann architecture and Harvard architecture. Okay. Thank you.